Hello all, and welcome back to the IoT mini-conf. I'm sure our next presenter needs no introduction, but I'll do one anyway. This is Damien George, the creator of MicroPython, here to talk about how to write fast and efficient MicroPython. Thank you very much, Damien. Please welcome to the stage.
Okay, thank you. Thanks everyone for coming to my talk. It's great to be up in Sydney this year. I'm Damien George. About 5 years ago, I started writing MicroPython. I think it was the 29th of April, 2013, I wrote the first line of code, and I actually wrote the date down when I wrote it, so I don't know. So I would remember, I like to date things. But so more than 5 years ago, I started writing it, and it's come a long way, and probably a lot of you have heard me talk before. But if not, I'll just give a brief overview of what MicroPython is for those people who are new to it. So it's a complete re-implementation of Python, so from the ground up, written in C. And the idea when I was writing it was to not look at CPython and how it was written, but just look at the language specification itself and try and copy the language specification and implement that. And so that way I could generate new ideas about how to solve the same problem in a different way, as in to implement Python. And the way MicroPython is written is so that it doesn't use resources, it doesn't use RAM, and it tries to be efficient with the way it does things so it can run in really, really tiny systems, like with 16 kilobytes of memory. And so the key thing is that when you log into your microcontroller, you get a Python prompt, and you can blink LEDs with one line of Python code, and it's an immediate response. There's no compilation and flashing of firmware like you're familiar with normal microcontroller programming. So it's quite fun and immediate and easy to debug things, but you can also write quite complicated applications. And there's lots of hardware that you can try it out on, and you can also try it out online with a simulator and download the code and have a lot of fun with it. So my talk today is going to be a little bit technical and a little bit fun and some few demos. So I have a background in theoretical physics, and in physics there are the concepts of time and space and energy. And if you try and extend those to computing and stuff, so time is like you want to make things go fast. Space is like storage, like hard drive storage and memory, so you want to reduce that. And the energy use, well, you all know about energy and how expensive it is and how you want to sort of reduce energy use. Because if we have 1 million or billion IoT devices and they use a nanoamp, that's really good. But if they use an amp, that's a lot of power. So any optimization you can do is good for the environment, as my son would like to say. So the aim of this talk is to just give a little bit of an overview of some technical details of MicroPython and how they relate to efficiency. And give some based on that insight, give some tips and tricks on how to make things faster if you're writing code. And some of these tricks will also be useful for normal Python and even programming in general. And then there's a few examples just to sort of motivate this whole thing. And I'll start with those two examples. So the first one, the very simple thing, the hello world of microcontrollers, is to blink an LED on and off. And in the top little black box there of demo code, so this will actually work. So it's creating an LED, the blue LED, and then it's doing a simple loop, so n times, so you'd have to feed in the parameter n, and just turning the LED on and off. So it's quite straightforward about what it's doing there. And if you run this on a Pi board, you can blink at about 50 kilohertz. So that's 50,000 times per second this loop can run. As in it will go on 50,000 times and off 50,000 times. So the loop runs 50,000 times per second. But we want to make that go faster. And so by the end of this talk, I'll show you how to make that go 500 times faster. And the second example is to read a file. So it's pretty silly. It's just reading data from a file there. So it's going through and reading 1,000 bytes at a time, n times, and then seeking back to the start of the file just to time itself. And that currently, just as it is, runs at about 1.5 megabytes per second in reading, and we can get that up to about 20 megabytes per second with very simple optimization. So keep that in mind. So the motivation of this talk is to make these things run faster, and I'll sort of go into some technical details, and we'll come back to making those speed up at the end. So this is a diagram of how MicroPython works internally, and don't try and absorb the whole thing. Just sort of understand that on the there's a compiler. So on the left is sort of the compilation phase. So it takes your script, which can come from one of those red boxes. You either type it into a prompt or you have a script in a file. And the lexer turns it into tokens, which gets parsed into a parse tree and then compiled. And the compiler can emit bytecode, which is run on a virtual machine, or it can even emit machine instructions. So that's, from JavaScript, perhaps you've heard about just-in-time compilation and making JavaScript really fast. They do that by emitting machine code. So MicroPython can do that as well, although it's ahead of time compilation. And I'll touch on that a little bit at the end. And then on the top right, that orange box represents all the runtime support functionality, like searching if a string ends with something, or splitting a string up, or searching in a dictionary. So all that sort of gory details. It's all written in C. It's pretty boring, but it's the guts of everything. So as I said, we have a compiler and just reads a input string character by character. So that means it doesn't actually load stuff into memory. If there's a file on the disk, it just reads it in 1 byte at a time. So it doesn't waste memory loading at all at once. But once you've run the compiler, it can leave memory fragmented because there are some structures it has to have in memory. So that's one thing to keep in mind. And also, any variable names that you use are left in RAM as well. So the more variable names you have and the longer they are, the more memory you'll be using at the end. So one way to optimize that is to use shorter variable names and reuse them. And when we generate bytecode, we also use RAM, obviously, to generate that bytecode. You can't really get around that. And as I said, we can generate machine code, which will make things go faster, and I'll show you how to do that. And also inline assembler is something if you really want to go very fast, and I'll show you how that will work with the LED example. So these are all of the bytecodes that MicroPython has when it compiles a script. Now, you don't have to understand all of these, but this is a list of them all, so you can see that there's a finite number, and they're not that complicated. A lot of them are to do with loading objects, false, none, true at the top left there. So when you have false in your code, that corresponds to 1 bytecode. So 1 byte to load false, and then do something with it in an expression. Down the bottom in the middle, there's call function, call method. So there's a bytecode to actually do that, and that's split up into one that calls simple functions and one that calls more complicated functions with variable keyword arguments, like when you use star and star operators. And then, there's a bunch of other things there. But all these things here can implement all of Python. And to show you a bit more of a concrete example, so here is some script on the left and bytecode on the right. And you can see this exactly what it's doing here. So it's loading the print, loading a string sleep. Now, load fast 0 means that it's loading the variable d, because that's the 0th local variable. And then it calls the function. So it calls print, that first thing it loaded there. And then the result doesn't care what the result is, just not using it. So it pops that off the stack. And then it does the next line, which is gets time, loads the sleep function, loads d again, calls the sleep function, discards the value with the pop top. And then the last 2 lines are returning none from this function. So that, you can see that takes 2 bytes to return none. So this whole function is 22 bytes in memory. And this kind of shows the differences in speed that you can get from certain things. So loading a global like print is slow because it has to go into the global dictionary and search for print. But if you look at the third line, load fast 0, this is just a 1 byte instruction, and it knows that d is the first local variable on the stack, so it can get it straight away. There's no searching through a dictionary. So loading local variables and storing to local variables is a fast thing to do, but global variables are slow. So that's probably the most important thing when you want to optimize your code, is to use local variables and not global variables. And the other thing is that it's slow to load methods and functions. So down the middle there, load method sleep. So you've got the time module, and I'm looking for sleep. So that also has to be a dictionary search. So it's got to go through a dictionary of the time module and look for the sleep function. And even though it's using hashing and it's sort of order 1, it's still slow, relatively. And so these things here can be optimized by sort of preloading any methods that you want to use over and over again if you want to make it faster. So yeah, this is kind of a good example of some real-life things that can help you make your code go faster. So the other thing, so this is a long slide, but don't get overwhelmed. It's just about memory allocation, which is really important in microcontrollers because when you allocate memory, it's slow because you've got to go and find some memory. And if you can't find it, you've got to do a garbage collection. So that can take 5 milliseconds or something, which is a long time when you want to flash an LED millions of times per second. So the best thing to do is to try not to allocate memory when you can. And to know how to not allocate memory, you've got to know what things don't allocate memory. So a little expression like 1 plus 2 times x and so on. Expressions don't need to allocate memory because they use the stack. And all of the basic statements in Python, as in when MicroPython implements them, like if and while, and for statements and try, except, finally, they don't need to allocate any memory on the heap, so they're all relatively fast. So you can do a lot of stuff without allocating memory. So this is heap memory. It still uses the stack, but the stack has been pre-allocated for the function. As I said before, local variables, because you know a local variable where it lives, it's easy to store and load local variables. Small integer arithmetic, if you're using less than 31 bits, that doesn't need to allocate on the heap. And then for things like lists and dicts and byte arrays, if you do in-place operations, like you're subscripting a dictionary or subscripting a list, or even sorting a list in place, those things don't need to allocate heap memory. So that's also good to know. So you can do quite a lot of things if you've pre-created things like lists and dictionaries. If you call functions and methods and you don't use the star or star operators, then that also doesn't allocate memory. So as soon as you go into the land of variable keyword and variable positional arguments, then you'll see slower code execution. And a lot of built-ins don't need to use the heap memory. But things you can probably imagine that do use heap memory is when you import a module, because there's a whole lot of compilation and importing and loading of dictionaries that goes on there. When you define a function and a class, again, you've got to create the actual function and class, so that takes memory. And one thing that trips me up, even though I know it, is that assigning a global variable for the first time will allocate memory. Because when you write to a global variable, you've got to store it into the global dictionary. And if the global dictionary is too small, it has to be resized, and you've got to find a slot for it, and so on. So that's something. Global variables are things you should try not to use if you're concerned about efficiency. And creating data structures is also, obviously, allocating a list is going to take memory. So the next few slides give some tips based on this knowledge that I've just gone through, of how to make things run a little bit faster. So as I said, use functions. Don't use global scope, so put stuff in a function if you can, because that will use local variables. So immediately taking something that's in the global scope, like in the module level, and putting into a function, that will make it faster. Preload or cache methods and functions that you know you want to use a lot. And sort of going against maybe some good programming principles, prefer long expressions rather than breaking them up, because a long expression doesn't have to load and store to some variables intermediate. It just creates this expression on the stack. So if you can write something in one line, write it in one line, because it will be faster. And don't write your own starts with function. Like if you want to search for the beginning of if you want to know so a string starts with something, use starts with, because starts with is written in C, and it's going to be faster than the way if you try and write that in Python. And MicroPython includes this way to make constants. So if you use this construct here from MicroPython import const, and then x equals const1, wherever the compiler sees x, capital X again, for this example, it will replace it with 1. So it's kind of like C hash defined or something. So it'll actually do proper constants there. And also, it is okay to do things like 1 plus 2 in your code. You don't have to optimize that to 3. The compiler will optimize that for you. So don't be afraid to use constants in ways like that. So to reduce RAM usage, just try and basically use the constructs that don't use heap memory. Use shorter variable names and reuse them. Okay, this is again against sort of some programming principles, but it's okay to use x, y, and I. If you just got coordinates or indexes, and if you're reusing a variable name that already exists somewhere else, you don't have to allocate more memory to sort of store that variable name. So use short names and make them. You're programming on a microcontroller, so don't be like this variable is the x coordinate of my window. So it's like just call it x. Temporary buffers. So sometimes it's good if you really don't want to allocate any memory on the fly, you pre-allocate it like a byte array of size 1 even, and then use that again and again. So you want to construct a command that's 1 byte long. You can do that by reusing a buffer. And the into methods, so I'll go through those with the file example, but there are some in-place reading methods like read into, where you read into a pre-allocated array and you don't have to create one on the fly. Don't use star or star args if you're concerned about speed and memory usage. And one way to improve compilation time, so you can pre-compile your scripts to pre-compiled MPY files. They're like PYC files, but from MicroPython. So that contains pre-compiled bytecode. So when you load that or you import such a script in, you don't need to do any compilation. So you save a lot of memory and a lot of time doing that. It still needs to load the code into memory, but it doesn't have to go through the whole process of compiling. So that saves you memory. So that is a big way to improve your speed as well as memory usage, is to pre-compile scripts. And then finally, you can actually, given a Python script, you can freeze it into the firmware. So you've got to do this at compile time with this when you're compiling in C. But this way, it uses almost zero memory because the bytecode will be stored in flash storage. So it doesn't use any RAM at all. But that's quite an advanced topic. But it's very useful if you've got big scripts. OK, so I'll try and show you how to make this script faster now using this knowledge. So the first thing we want to do, like I said, is to put it into a function. So I'm just going to switch here. So LED 1. All right, so this is the simple loop here. So all the other code, down here at the bottom, it's just doing timing and printing out the timing of the loop. But the actual code here we've got is just this simple loop to turn the LED on and off. So if I run this code on my Pi board here that I have connected, so LED 1, so it will tell me, I'll scroll the screen up. So it runs at about, 57 kilohertz. Now, if I have a look at LED 2, so what I've done here is simply put this in a function. So I've done the same code, taken the same code, and I've just put in a function. So I've changed nothing else. And I've got some other, there's just timing-related code down here, so ignore that. But the main code here is just this blink simple function. So if we run this one, run number 2, I'll just, no, that's not what I expected. Sorry. OK, so 66 kilohertz. So we've gained, from 55 to 66, we've gained a little bit. But sometimes that's all you need, because you just need it to run that little bit faster. Gaining 10% in speed is actually quite big, just by putting something into a function. So that's because it didn't need to use global variables. OK, now, in the third case, so we're going to, it's still in a function, and we're going to preload the methods that we want to use. So on is LED on. So what it's doing here, it's taking the LED object, which was a global variable, preloading the method on, and storing that into a local variable. So as I said, local variables are really quick. So now down here, when we call on, it's loading a local variable, which is 1 byte, and very quick, and then calling it straight away with no arguments. So it's super quick. And there's no dictionary lookups for globals, no dictionary lookups for methods. So you can expect that this might actually run quite fast. Oh, and I've also optimized the range. Yeah, that's another little trick that you can, yeah. It's a bit faster if you do the range this way, but you can ask me about that later if you want. So, oops, give away too much there. LED 3. All right, so that went to 182 kilohertz, so that's 3 times faster. So you can see that there's a big difference there by preloading your methods and using local variables instead of globals. So the difference there between 60 kilohertz and 180 is looking up things in dictionaries, really. Okay, so now we get, so so I think LED 3 is probably like where you might stop in most cases, and you're like, it's still understandable. And if you really want to optimize stuff, this is how you go. But if you want to go further, so I mean, you can use the standard technique of loop unrolling. So we'll unroll the loop 8 times, but everything else is the same. I've preloaded my methods, it's in a function. Divide by 8 here, because obviously I unroll it 8 times. And yeah, so I'll just unroll it 8 times. So let's see how much faster that goes. So what is that, 10% again? No, it's not too bad. But what you can see here is you're really hitting the limit of the virtual machine interpreting bytecodes. So there we're sort of getting rid of the overhead of the loop. So let's see how much further we can go. LED 5. Sorry. So, okay, so what we're using here is, as I alluded to before, we're using machine code and not bytecode anymore. So when this function executes, or first of all, it's compiled into machine code. So instead of now running a virtual machine, actual instructions on the hardware, this is a little ARM chip, are being executed each time. So to do an on, instead of executing the on bytecode, instead of executing a few bytecodes to load the on method and call it, it's executing actual machine instructions directly, which makes things, yeah, a little bit faster. So we'll see how much faster. LED 5. So this is the same as LED 4, exact same code, but it's in machine code instead of using the virtual machine. So that's about 20% faster. So it's pretty easy to just put this little decorator, there's a one-line change, this decorator here, at the top of your function to make it machine code. Not all things are supported, but a lot of things are, and I'm improving that. So I think there's 2 more to go. Hang on, so LED 6. So this one here is really a bit crazy. So this uses another mode called Viper mode, which is a bit undocumented and not finished, but it still does work. It allows you to basically directly do things in machine code, but write it in Python. It's really kind of a weird hybrid of Python and C. It's like Python syntax with C semantics. So what I've got here, I've created a pointer that points to the register of the peripheral. So we're on GPIO B for this LED. You could actually see LED flashing 50,000 times a second if you wanted to down here, but it's a bit boring. So this is actually, each line here, it's going on and off. And by writing to a register. So this is going to turn into basically one machine instruction. So it's going to do one instruction here per on and off, as opposed to loading a method before and executing it. I don't want to go into the details of this. You can ask me about it later. I just wanted to show you what is possible. So if we execute this one, it's, yeah, I can't even multiply that, do that division in my head. It's quite a lot faster there. So it's more than even 10 times faster. It's 60 times faster almost, or 50 times faster. So I'll just show you that code again. You've got to know what you're doing, and you've got to be able, you can't read files this way. You can only do things that require register access or really low-level stuff. But yeah, I'm just writing to the register here, and that's it. So then there's a final example, LED 7. So this is written in inline assembler. So so logical shift left, so that's divided by 8 like before. Load the value of this load the value of the peripheral register into R1. one shift left 4, you saw that before. That's the, because we're GPIO B4. Loop is the label. And then this store high, so that's actually turning it on and an off, on, off, on, off. So I've unrolled the loop 8 times here, and at the bottom, subtract 1 from our counter, and branch if it's not 0 back to loop. But if it is 0, we've finished our loop, and then that's the end of the function. So here I've written inline assembler in Python syntax. And so this is sort of the punchline of the entire talk. So 27 megahertz, right? So that's about 500 times faster than the initial code. And 27 megahertz blinking LED is almost the limit of the actual microcontroller itself, because we're writing, like, it's just, that's because it runs that fast. So the microcontroller runs at 168 megahertz here. So, you know, you're doing less than 10 instructions per blink. So yeah, that's that. And then I've only got a minute left, but doing this next example was pretty quick. So this is just reading 1,000 bytes over and over and over again, and we're reading at 1.5 megahertz, or sorry, 1.5 megabytes per second. File, okay. I've got everything here in one file. So the naive implementation is this file read here, which is just what you saw on the slide. The optimized one, I've unrolled the loop twice, and I've preloaded the methods. So they're just some techniques there. And then the final optimization, the third one, it's simpler, but what I've used here is this read into method. So basically, this is not allocating memory each time. So the other example was allocating 1,000 bytes every time it read it. But this example, the one that's going to be the fastest here, I've pre-allocated that array on that line. And then in the actual loop, which is just this bit, I've used the same array and just read 1,000 bytes into that same array. So this thing doesn't use any memory when it's running. It doesn't allocate any additional memory. So if we run that, it'll run all 3 of them and show you the comparison between them. So the simple example, 1.5 megabytes. The slightly optimized one is almost not faster at all. That's because you're really limited by the memory allocation here. But then if we don't do memory allocation in the loop, we get up to 20 megabytes a second, which is about 12, 13 times faster. And that's really as far as you can go. That's almost the limit of actually reading the flash memory itself. So, but the key here is that showing you that RAM allocation is quite slow. All right, so I'm really at the end of my talk now. And just to mention that the other optimizations, so energy use, if your code runs faster, it can sleep for longer. And sleeping is really low power consumption, so therefore use less energy. That's a pretty simple rule of thumb. But then you've got to think about other optimizations, like how long did it take you to code it, how long does it take you to debug it, and how long does it take you to maintain this thing. So you've got to make sure you only optimize things that really need to be optimized. And I think that's sort of the key thing that you say to any programming language is that optimization should be at the end, after you've worked out what the bottlenecks are. The basic rule of thumb I use is that when you write something directly in Python, it's about 100 times slower than if writing the same thing in C. But you can usually do a lot better than that because you don't read a file 1 byte at a time in Python. You call file.read and read 1,000 at a time. And that's all done in C under the hood. And so reading a file is not 100 times slower in Python than in C. So try and use runtime methods, like reading files or string or ends with or starts with on strings, or regular expressions. And in MicroPython, the key thing is to use local variables and not global variables. And that will get you a long way to making things faster. So thanks for listening. Some links here. And yeah, I welcome any questions if I've got any time.
So we've got just about 1 minute left, so we might have a chance for 1 or 2 quick questions if anyone's got some.
Hi, Steve Gale here from the Gordon.
Yep.
Just a question on when you pre-allocated the function into, where you pre-allocated the function, it looked like it was locally. Just wondering how that actually works. I've never seen that.
You mean like in this one, or so?
It was where you had the function pre-allocated locally.
Oh,
inside
okay,
the-
I see what you're saying. Yep. So this one?
Yes. Just interested to know what's actually going on.
So so LED itself is a global variable in this function because it's not, it's defined in the global scope.
Oh, right, yep.
So when this function is compiled, it has to look up in the global dictionary of global variables to find LED. And it may not exist, so it may have to raise an error and so on. So it's got to go and search for a function by name. But what I've done here is I've loaded that name once, and then I've also loaded its method. So I've done another dictionary lookup to load the method from within the object. And that returns a bound method. So in Python you have like, if I have a string, and starts with, so this is that's a bound method of an instance of an object. And then I can call that, so, yeah, but I haven't given it any arguments. So this is actually it's preloading a method and storing it into the local variable on. So on is a local variable. So when I do this on here, it's very quick, and it's much quicker than doing LED.on, even though it looks kind of very similar. So, yeah.
Fantastic, thank you.
So I think unfortunately that's all we've got time for now, but I'm sure Damien will answer questions in the short 10-minute changeover break, or you can find him out and around PyCon. Thank you very much, Damien.
Okay.